Okay, welcome to Lesson 11 of Module 6, Using Linear Models in a Data Context. Okay, so in the previous lesson, Lesson 10 was about linear models, and we talked about the different names for the different variables, dependent, independent. We talked about the meaning of the slope, and we're going to do that still again. This time there won't be exact functions, mathematical rules for these. We'll be fitting our own line to the data once again. So we'll have scatter plot data that we'll write an equation of the line, and then we'll talk about what the slope means. And we're going to use some specific language and make sure to reference both variables when we do that. All right, so let's look at our first example, exercise 1. Old Faithful is a geyser in Yellowstone National Park. The following table offers some rough estimates of the length of an eruption in minutes and the amount of water in gallons in that eruption. Chang wants to predict the amount of water in an eruption based on the length of the eruption. What should he use as the dependent variable and why? Okay, so before you pause the video and think about that question, let's look at the data. So what is this saying? It's saying that one time the geyser erupted for a minute and a half and 3,700 gallons was estimated to have come out of Old Faithful. In 2 minutes, there was 4,100 gallons that came out. That's a lot of water in a short amount of time. So we have these 4 data points. Okay, so what we want to know is if we want to predict the amount of water based on the length of an eruption, which one would be the dependent variable and why? Okay, so go ahead and pause and think about that. Come back and we'll talk about it together. Okay, so in the last lesson we saw that the dependent variable is the quantity that we are predicting. So in this case, the dependent variable, because it's the quantity that we're predicting, would be the amount of water. Okay, so in gallons. Gallons of water is the dependent variable. Therefore, the independent would be the time. Now, it's not like we get to decide how many minutes Old Faithful will erupt for. A lot of times in a scientific experiment, we think of the independent variable as the thing that we get to choose values for. But in a sense, we are choosing values here. So we want to say, if I have an eruption of 2 minutes, how much water am I likely to get out? How much water is likely to come out of the geyser? Okay, so independent variable is length of the eruption in minutes, and dependent is the amount of water in gallons. Okay, so let's look at some scatter plots here. So here's 2 possible scatter plots. They look similar, using the same 4 data points. But notice what's different about these 2 scatter plots. The points are in different places, but that's because of how the axes are written. So in this first one, we have amount of water in gallons and length of eruption in minutes over here. And on this one, we have it in the opposite way. So based on what we said about the variables, which one of these should Chang use to build his prediction model? Remember, he's predicting the amount of water based on the length of the eruption. Okay, so the thing that we're predicting should go on the vertical axis. That would be the dependent variable, and the independent variable should be here. So we said the independent variable was the length of time, and the dependent variable, or the thing that we're predicting, is the water. So this is the scatter plot that we want, this one right here. Not that one. Now, they could both be used and both have meaning, but we want to think about it in terms of what we're predicting, which is going to be the amount of water. Okay, so that's the one we're going to use. And next question says, suppose that Chang believes the variables to be linearly related. And it does look like a linear relationship. The amount of water is increasing as the time of the eruption increases. Use the first and last data points in the table to create a linear prediction model. Okay, so let's write down what those 2 points are. We've got the points 1.5. Oh, oops. 1.5 minutes and 3,700 gallons. Now remember, always writing independent variable first, dependent variable second as well. Okay, and then the second point, or do we want us to use the last point? So 4.5 minutes, and the eruption was 8,400. Okay, so to find the slope between those 2 points, so remember, I'm going to write this as y equals mx plus b. So I need to find the slope first thing. So the slope is the change in the y variable. So this is going to be 8,400 minus 3,700 divided by the change in the x variable, 4.5 minus 1.5. Okay, so that's something, 4.5 over minus 1.5 is 3. And then 8,400 minus 3,700 4,700. And when I do that division, I get approximately 1,567 gallons per minute. Okay, so what is that? What is that slope value telling me? Telling me that every minute that Old Faithful is erupting, another 1,567 gallons comes out of it. Okay, but that is our slope. So in order to solve for the y-intercept, we need to put in a point. So we'll do the first one. So y equals mx plus b. Let's write that again. Let me get a different color here. I'm going to cram this together. So we've got y is equal to mx plus b. So we can put in 3,700 for y. And our slope is 1,567. And that's times x. And let's put in x too. The x that goes with 3,700 is 1.5. So times x would be times 1.5 plus b. And then I want to do the multiplication here. Subtract it from 3,700 to get b. And so we're going to get that b is equal to, let me look at the math here, 1,350. Okay, so our linear model that predicts the amount of water, I'm going to write this, I'm going to just write it down here. Sorry, I'm going to write it in the other space, is y is equal to the slope, 1,567, slope times x, plus the y-intercept, 1,350. Okay, so that's my linear model. I should have written it up there, but I didn't have room. Okay, so we could use this if we plug in a time value for x. This will tell us, remember x is time of the eruption, and then multiply that by the slope and add the y-intercept, and I will get the amount of water that comes out of Old Faithful in that amount of time. Okay, so that's a prediction model. Remember, we wanted to predict the amount of water, and that's what this function is going to do for us. Okay, so part D says, a friend of Chang's told him that Old Faithful produces about 3,000 gallons of water for every minute and that it erupts. Does the linear model from part C support what Chang's friend said? I want you to think about it for a minute. Pause and then come back and we'll talk about it. Okay, so our slope tells us something. It tells us that for every minute, we could even say for every additional minute of eruption, remember that's what gallons per minute means. For every additional minute, Old Faithful produces 1,567 gallons. Okay, so for every additional minute, Old Faithful produces 1,567 gallons. So our friend is wrong. So Chang's friend is wrong. He might be thinking of a different geyser. We'll say he's mistaken. There might be another geyser that produces 3,000 gallons every minute. Okay. Part E. Using the linear model from part C, does it make sense to interpret the y-intercept in the context of this problem? Explain. So here's our linear model. Y is equal to 1,567 times x plus 1,350. Okay, the y-intercept is the point where x equals 0. So this would be y equals 1,350 gallons when x equals 0 minutes. Okay? That's what the y-intercept is saying. Does that make sense in the context of this problem? The answer is no. The y-intercept does not make sense. Why? Does not make sense because if the geyser erupts for 0 minutes, then there's no water coming out. Whoops. geyser. There would be no water produced. So this linear model works over a certain range. Okay, it's not that it's wrong, it's just only fits over a certain range of values for x. And that's fine. We don't need them to work for every value, but what would that line look like that we just wrote the equation for? It connected those 2 points, so it's basically right there. That's a pretty good fit. It's close to all the points. There's two of them are right on, one's above and one's below. Okay, let's look at our next example. Okay, our next exercise has to do with the times for the men's 100-meter race in the Olympics. Okay, so the following table gives the times of the gold, silver, and bronze medal winners for the men's 100-meter race in seconds for the past 10 Olympic Games. All right, so you'll see the years starting with 2012 all the way down to 1976. And you can notice the times, and you can kind of see a trend in this table just by looking at the numbers as we go back to 1976. But let's look at part A first. If you wanted to describe how mean times change over the years, which variable would you use as the independent variable? And which would you use as the dependent variable? Okay, so remember the dependent variable, which is also on the vertical axis, is the thing that we are going to want to predict. Okay, so what this is saying, I'm just going to restate, is that mean, whoops, I still have my arrow there, mean or average, right? Mean medal time, and this is the average of the 3 medal winners. Mean medal time depends on, or is going to be predicted based on, mean medal time is predicted, or we're saying it can be predicted based on the year. Okay? And if you don't think there's a trend, look in the table. What's happening as we go? What happens to the time for the gold medal winner as we go back in time? You can notice in general what's happening here. Okay? You should see the time as we go further back, the time for this race increases, which means they were generally, runners are generally slower here than here. Okay? Draw a scatter plot to determine if the relationship between mean time and year appears to be linear. Comment on any trend or pattern you see in the scatter plot. So take some time, and we're only you're only graphing the mean time here, right here. You don't have to graph all the gold, silver, bronze, okay? So the scatter plot is going to be mean medal time based on year. So before you go off to do that, let's talk about what's going to go where. So mean medal time is the dependent, right? I guess I didn't really finish talking about that. It's dependent because it's what we're going to predict, and the year is the independent or the predictor. Independent, or the predictor variable. Okay, so we're going to have year on the horizontal axis, and we're going to have mean time on the vertical axis. Now, if you're going to use the numbers for the years, then you probably are not going to start right at 0. So you would have kind of that break, and then you'd start here with 1976, right? And so on. So, okay, so go ahead and construct a scatter plot, and we'll see, come back and check yours against mine. Okay, here's a plot that really shows the trend in this data. So a couple things to notice is that they really stretched out the scale here. The times go from 9.7 all the way up to 10.3, and they've left the bottom part of the scale off so that we can really see the detail in the trend of the shrinking times. In a race like the 100-meter, every 1/10 of a second is really significant, okay? They're going to measure out to hundredths of a second, as we saw in the data table. So every 1/10 of a second is very significant. Okay, so we see this negative linear trend right here, don't we? All right, so if you had the scale too scrunched, you might not see the trend as much. It's really dependent on having the scale properly done. Okay, so there is a possible scatter plot. Yours could look slightly different, but hopefully you can see that trend. Okay, part C says one reasonable line goes through the 1992 and 2004 data points. So let's find the equation of that line. And let's draw it as well. So we're talking about the 1992. We're going to draw the line through this one and through that one. Okay, so there's the line, and now we're asked to find the equation of that line. Okay, so to find the equation of the line, once again, we're looking at y equals the slope times x plus a y-intercept. And the 1992 data are 1992. The mean time was 10 and 100th. And in 2004, the mean was 9.86, 9 and 86/100ths. Okay, so if we want to find the slope, once again, we're looking at the difference in the y. So I'm going to we'll go the other way. 9.86 minus 10 and 100th divided by 2004 minus 1992. Okay, so how many years was that? From 1992 to 2004 was 12 years. And the difference in the times is, okay, and that's a negative 15/100th. So in 12 years, the mean time decreased by 15/100ths of a second. Okay, and so if I do that division, I get negative 0.0125. Okay, and that would be seconds per year. Because remember in the denominator, this is seconds, this is years. So the units on this number here is seconds per year. All right, so what's our linear model then? So we've got our slope for that. Now we need to find the y-intercept. So to do that, we use a data point, and we'll use the 1992. 1992, except that doesn't go there. 10.01, because this is the y, is equal to negative 0.0125. You're getting so much experience finding the equation of a line using 2 points by doing these scatter plots, right? We did that, but now you're really using it, plus some y-intercept here. Okay, so if I solve for that y-intercept, I get 34 and 91/100 is my y-intercept. So my linear model is going to be this y equals mx plus b, and I'm going to put my m and b in there. So I'm going to get y is equal to negative, now we wanted a negative slope, right? Didn't mention that before, but it should be a negative slope because it's a negative trend on the points, plus 34.91. Okay, so once again, this equation here now is, I can put in, for x, I can put in the value of the year, and y will give me a prediction for the mean medal time for the Olympics, for the men's 100-meter race. Okay, so let's talk about this though. Does this y-intercept make sense in this case? So in the year 0, the mean time was 34.91. Okay, so first of all, there wasn't an Olympics in the year 0, and probably that's not a good prediction, right, for this 34.91 for a mean time for that race. I don't think people were that slow that long ago. So let's look, but we'll come back to that in a minute. So let's look at the next question here. Before he saw these data, Chang guessed that the mean time of the 3 Olympic medal winners decreased by about 0.05 of a second from one Olympic Games to the next. Does the prediction model you found in part C support his guess? Okay, let's write our prediction model up here just for reference. Okay, so there's our prediction model. So he guessed 0.05 of a second from one Olympic Games to the next. Just looking at the data, he was thinking about 0.05. Okay, let's go back and think about our slope once again. So what's happening is that for every change of 1 year, the mean time decreases by 0.0125 seconds. Okay, how does that go along with 0.05 seconds from one Olympic Games to the next? Well, if you look, you notice, and you probably know this anyway, that it's 4 years from one Olympic game to the next. So let's look at the slope. So what our slope is telling us is that we have a decrease of 0.0125 seconds every year. Okay? But the next Olympic Games only comes along every 4 years. So we need to multiply that by 4, and what we get here would then be negative 0.05 hundredths seconds in 4 years. Okay, so he was right in his prediction. His prediction is supported. And it's supported because 0.125 seconds per year is the same as 0.05 of a second every 4 years. All right, so if this trend continues, I'm on part E now. If this trend continues, what mean race time would you predict for the gold, silver, and bronze medal winners in the 2016 Olympic Games? Explain how you got this prediction. Well, how can we said that our linear model is for making predictions, right? So pause the video and make a prediction for 2016 by plugging that in for the year and predict the time. Okay, so the time Y is going to be negative 0.0125 times the year 2016 plus 34 91 hundredths. So I'm going to use my calculator and I'll find out that the predicted time, make sure you get the negative sign there, the predicted time is going to be 9 71 hundredths seconds. Okay, and hopefully you're thinking about why are the mean times decreasing? If you know much about racing, we're getting better equipment, we have better shoes, we have better training, and our athletes just keep getting faster and faster. So that's what's happening. And here's a little bit of Olympic history for you here. So the data point 1980 and 10.3 appears to have an unusually high value for the mean time, 10.3 seconds. Using your library or the internet, see if you can find a possible explanation for why that might have happened. Okay, and I'm not going to tell you, but let's go back and look at the data. We'll look at our plot here. Here's 1980. That is one point that would really throw the data off. Seems really high. So the runners were slower this year, right? It took them longer to run the race. So what was going on in 1980 that might have caused that? And I'll give you just a hint so that you'll know when you've found the right answer. It has to do with who was at the Olympics that year. So look it up. Google 1980 Olympics and see what you can find on that. Okay, before you head off to the problem set, I want to show you something that is commonly done with these functions, and this would be a way to make the y-intercept make sense for this problem. So notice this is the same data table that we had for the 100-meter race, mean medal times, except that they've changed how they number the years. So what they've done here is they've started with 1976 being year 0, 1980 being year 4, and so on up to 2012 being year 36. So then 2016 would be year 40. Okay, so instead of the actual number of the year, we've said number of years since 1976. Okay, and if you do this, then using the data points for 1992 and 2004, you come up with a different model. You get y equals 10.21 plus negative 0.0125x. So the slope is the same because the difference in years is the same, but the y-intercept becomes different, okay? The y-intercept is now 10.21, and it does actually make sense. Okay, so the y-intercept would be the mean medal time in 1976. Okay, now notice it's not, it was actually 10.09. Our linear model predicts 10.21 because remember, our linear model only exactly matches these 2 points. It's predicting the rest of them. Okay? All right, so let's talk about what we've seen. So lesson summary. In the real world, it's rare that two numerical variables are exactly linearly related. But if they're roughly linear related, then we can draw a line through the data and use the line to make predictions and answer questions. Remember, and I mentioned this before, that now we're just informally drawing a line, but later you will have a formal mathematical method for determining the equation of a best fit line. Okay, so good luck with the problem set, and we'll see you back here for lesson 12. Lesson 12 is going to be an optional lesson. So if you feel like you have a lot of, time, then you should do it. Otherwise, feel free to skip it.